Hello students. Today we're doing a set of notes on studying populations. You should have your Cornell notes in front of you, and in your topic/objective you're going to write studying populations. For today, we're not going to just have one essential question. We're actually going to have three. So in your essential question box, you're going to need a little bit of extra room. If you have to go into the notes, that's okay. The first essential question is, how do ecologists determine the size of a population? So how do they know how many members are there? What are the ways they can do that? The next question is, what causes populations to change in size? How come they grow? How come they shrink? So what causes populations to change in size? And the last questions is what factors limit population growth? So what are the things that keep a population from continuing to grow without stopping? So in our notes section, our first heading is going to be determining population size. Okay. So I like to have, because it's a heading, I like to center it. I have it capitalized and I have it bolded and underlined as well. So make sure it stands out in your notes too. Now, our book really just focuses on 4 ways of determining a population size. Please know that there are more ways of determining a population size than just the ones provided by our book. So these are the ones provided by our book. Some methods, notice it says some methods of determining the size of a population are direct observation, indirect observation, sampling, and mark and recapture studies. So those are the 4 we're going to be focusing on for the purposes of our work today. The first is direct observation. And direct observation is very simple. It's just as simple as it sounds. You're just directly observing the members of a species and you're counting them. So for example, if I wanted to know how many fish were in my fish tank, I'd just go over to the fish tank and I'd count each individual fish. So using direct observation, you're counting all the members of a population. This really works well if you don't have to count that many things and it's in a relatively small area. But if you were to apply this method to a very large area with a lot of members in a population, it really wouldn't work very well. So you wouldn't want to use it for something like counting all the trees in the Amazon rainforest. It just would be too many. So it's really reserved for small numbers in relatively small areas. An example from the book is if you wanted to know how many crabs were in a tide pool, you'd go right over to the tide pool and you'd just count the crabs, and that is direct observation. And because I'm hungry, I'm going to give you this example. If I wanted to know how many donuts were in this box, I would go over to the box and I'd physically count. There are 12 donuts there. Okay, so that is direct observation. Now, another way of determining a population size is through indirect observation. So in indirect observation, you're not actually counting the members of the population, you're counting evidence that organisms of a given species have been in an area. So you're not counting the organisms themselves, you're counting signs or evidence of the organisms and estimating the population based on that evidence. I'm going to talk a little bit about what this means, but before I do so, I want to make sure that you understand what the word estimate means. And when you're estimating, you're really just giving an approximation of a number, and that is based on reasonable assumptions. So I'm going to tab this over a little bit because it's under indirect observation. So an example that we can talk about is that if you wanted to figure out how many birds are living in the woods, it might be really difficult to go out and count the birds because they're flying around, they're coming and going, and it's difficult to know if you're recounting a bird. So instead, what you could do is count nests. So nests would be signs of the birds living somewhere, and you could estimate the population size based on that. So, for example, if you know there are typically 4 robins that live in each robin's nest and you count 20 nests, you could reasonably estimate there are probably about 80 robins living in a given area. But that is just an estimate. In the book, they talked about trying to figure out how many birds were living in a cliff, and it was a very, very busy cliff, and the birds were flying in and out, and it was too difficult to count each individual bird through direct observation, so they counted the number of mud nests in the cliff and were able to estimate the population based on that. So that's direct observation is counting all the members of a population. Indirect observation is counting signs of an organism and estimating the population based on that evidence. The next way to determine the size of a population. I forgot about indirect observation. I gave another example in class. If you wanted to figure out how many people were living in a neighborhood, you could count the number of houses and then estimate based on that. So if you knew that there were typically 4 people living in each house and you counted 100 houses, you could estimate that there are about 400 people living in a neighborhood. The next method of determining a population size is doing something called sampling. In sampling, what you're doing is you're counting the number of organisms in a small area, which is your sample, and multiplying to find the number in a larger area. Now, I want you to think about what the word sample means. If you went into an ice cream shop and you were trying to figure out what flavor ice cream you want, you might try a sample of a few things. Now, in a sample, you're not getting a giant scoop of a flavor. You're just getting a really small, a little small taste of it, and that way you can tell whether or not you like something. So you're getting a small taste to figure out if you want the larger thing. It's the same kind of thing with sampling for population size. You're counting the number in a small area and you're applying it to a larger area. An example that I give here, if you wanted to figure out how many apple trees were on a 100-acre apple orchard, whoops, I'm sorry, my picture has gotten in the way of my words. If you wanted to count the number of apple trees on a 100-acre orchard, you could count the number of trees in 1 acre and then multiply by 100 to get an estimate of how many trees are in the whole orchard. So if there are 35 trees in 1 acre, 35 times 100 is 3,500 trees. Another example I have here is that if you're trying to find out how many oak trees were in a 10-acre portion of a forest, you could find a sample area that's maybe 1 acre, and you count the number of trees in that area, and then you multiply it by 10 to figure out that there are approximately 60 oak trees in a forested area. When you're doing sampling, one of the things you have to be really careful of is that the sample that you're taking needs to be representative of the area as a whole. Let's go back to the ice cream example. If you're trying to get a taste of what bubblegum ice cream tasted like, and you got a little sample of it that didn't have any of the gum pieces in it, and maybe you're a person that doesn't really like things in their ice cream, and you thought, oh, well, this tastes good. And then you get your big scoop and you realize it has these big chunks in it and you don't like the chunks. Well, that sample you had really wasn't representative of the ice cream as a whole, was it? In class, we talked about if you're trying to figure out how many trees were in a forest, but you didn't realize that the forest also had a pond in the middle of it, you could really very easily make a mistake. So if you took a sample of the trees over here and you counted and you didn't realize this pond was over here, your sample is not going to give you an accurate estimate. So that's one of the things you have to be careful of when you are doing sampling. Okay, oops, sorry. So I want you to put that little note in your notes. For sampling to work properly, you need to make sure that your sample is from an area that is typical of the larger area. The the last way scientists can measure population by our book standards is through something called a mark and recapture studies. And mark and recapture studies are a little bit complicated, and I'm not going to go into a whole lot of detail about it, but I'm just going to give you a basic overview. Basically, what happens is that organisms are captured and marked and then released to the wild. And then at a later date, scientists will go back to the same area and they'll collect another group of organisms, and they'll count the number that have marks. So those ones that have marks are now recaptured because they were already captured before, and then count the number without marks. And they use the mathematical formula to then estimate the total number of organisms. It's actually kind of complicated, and we're going to do a little in-class simulation of that. But the basic gist is that organisms are captured and marked, released to the wild, and then captured again, and scientists can then estimate how big a population is. And so I have a little picture here. Little mouse, isn't he cute? He's got a little Sharpie mark on him. So scientists are trying to estimate the mouse population, capture him, they make a little mark, and later on they capture another group of mice and see how many have marks and see how many don't, and they can determine the population size based on that. Now, mark and recapture studies are not going to work for organisms that are stationary. So you can't do a mark and recapture study for things like trees or plants or fungus because they don't move. So if you mark them, and try to recapture them, well, they're not going to go anywhere in the first place. So that's really only for organisms that move around and can be big enough to be marked as well. That's another thing that has to be considered. Okay. So those are the four methods in which scientists can estimate a population. So how do they determine the population size? Direct observation, so you're counting all the members of a population. Indirect observation, where you're counting evidence of organisms and then estimating the population. Sampling, counting the number of organisms in a small area and then multiplying to find an estimate of the number in a larger area. And then mark and recapture, so you're capturing them, marking them, releasing them, and recapturing them, and using a formula to figure out how many are in the population. So keep in mind that of these four, only one of them is going to give us an exact number, and that is direct observation. Direct observation is the only one that you're not estimating. But if you do the other ones properly, indirect observation, sampling, and mark and recapture, you can get pretty close to a very accurate number, though direct observation is the only one that's not an estimate. Okay, so that's how we determine population size. Next, we have to look at, well, what are the things that cause a population size to change? So that is our next heading, changes in population size. And, oops, sorry about that. Okay, changes in population size. What are the things that cause a population to change in size? So populations can change in size when members join the population or when members leave the population. That's a pretty simple way to look at it. Okay, so how do things grow? Well, by getting more things. How does a population shrink? By losing some of those things. The two main ways that individuals join and leave a population is through by birth and death. Okay, so births and deaths. The main way in which new individuals join a population is by being born into it, and the main way in which individuals leave a population is by dying. Okay, and so there are two numbers that scientists will look at when they're determining a population size and trying to figure out why things are changing. One of them is birth rate. And all birth rate is the number of births in a population in a certain amount of time. So if I noted that there were approximately 10 mice being born per week, then that is the birth rate, 10 mice per week. Or you could say If you wanted to say there's 52 weeks in a year and 10 mice are being born in a week and you wanted to know the birth rate for a year, you'd say there were 520 mice being born per year. That is the birth rate. Number of births in the population in a set amount of time. And because I think they're adorable, I'm going to add a little picture of little baby bats in blankies that have maybe just been born and have joined a population of other bats. Okay, and so if you have birth rate, you also have something called death rate. And the death rate is just, you look at it the same way as you look at death rate. It's the number of deaths in a population in a certain amount of time, whether it be a week, a month, a year, a decade, or even a day. The number of deaths in a population in a certain amount of time is the death rate. And because it is close to Halloween, I'm going to give you a little picture of some spooky ghosts in a graveyard to illustrate what death rate might look like. But there are other ways for populations to change in size other than births and deaths. Well, how else? New members can join by just moving in, and members can leave by moving out. So although birth rate and death rate are the two main ways in which populations change in size, there are other ways as well. So organisms can come into a population by something called immigration. And I've underlined here, immigration starts with an I, as does the word in. So immigration means that members are coming into a population. And organisms can exit a population by something called emigration. And I know it's terrible, they sound exactly alike. But the difference is that immigration starts with an I, as does the word in. Emigration starts with an E, as does the word exit. So hopefully that'll help you remember what those words mean. Okay, now when scientists are studying populations and they want to know whether or not they think a population is growing in size or decreasing in size, they might look at the birth rate and the death rate. If the birth rate is greater than the death rate, they can reasonably state that the population size is going to get bigger. And on the flip side, if the death rate is greater than the birth rate, then you'll know that the population size is going to decrease. Okay, so I'm going to add that in. So if the birth rate is greater than the death rate, population size, guess what? It's going to go up. And if the death rate is greater than the birth rate, guess what? Population is probably going to go down. That sounds pretty reasonable, at least to me. Okay, next. All right, hold on one second. I'm just going to make it easier for myself in a sec. All right, here we go. One of the things that you might look at if you're a scientist looking at population is population density. And population density is the number of individuals in an area of a specific size. So if I wanted to know the population density of ants in a field, I might be able to count the number of ants in a square foot and then Okay, so the number of individuals in an area of a specific size is population density. So the number of areas per unit area is how they calculate it. So if there were 1,000 ants in 1 square foot, you'd have 1,000 ants per 1 square foot would be the population density of ants. Okay. Next, we're going to talk about, we've talked about, well, populations can grow by organisms being born, populations can shrink by organisms dying, they can also grow by organisms moving in and shrink by organisms leaving. Well, what is going to keep a population from just growing out of control? It's something called a limiting factor. So that's our next definition. Limiting factor. Limiting factor is our next definition. A limiting factor is an environmental factor that causes a population to either stop growing or to decrease. And there are three things that our book talks about. The first is food and water. It's pretty simple. Organisms require food and water to survive, and if you don't have enough of it, they can't live. And so either they're going to die out or they're going to leave the population. They're going to go elsewhere to find that food and water so they can survive. Now, organisms that can move around, it's a lot easier for them to just leave a population. But there are some organisms that can't move around, that can't leave. So an example is like maybe your lawn during the summer. I know my lawn during the summer, we don't go out and water it every day, and sometimes it gets hot and it doesn't have enough water and the grass dies. That grass can't just lift itself up out of the ground and walk around and go find a different place that has more water. It's just not going to happen. But organisms that do move around are able to go out and hopefully move and find a place where they can find those resources. But that still means that they have now left the population, and that has caused the population to decrease in size. The next limiting factor is space. Organisms need a place for shelter. They need a place to be able to find food, to find water. And if they don't have enough space, they can't stay in an area. There's only so much room. And so if it's overcrowded for some reason, or maybe they outgrow their space, they might have to leave. Or again, if it's an organism that does not move, it might die. So here's my space. You can't really fit any more band members in this bus. There's too many in there. They need space to be able to bang those their drums and to play their accordions. And so you can't fit any more in there. So organisms need space for shelter, just as the members of this band need space to play their instruments. And if you don't have enough space, you either have to leave, or if you're an organism that cannot leave because you're stationary and you're stuck in the ground, you might die. And last but not least, the last limiting factor is weather. Weather is our last limiting factor. Temperature and rainfall can limit population growth. So we talked about this in class. Like if you're talking about the Arctic Circle, there are certain things that just can't live there. There are certain populations that can't survive in that with those temperatures and with the amount of precipitation that goes on there. So temperature is going to affect whether or not populations can live in a certain area, and the amount of rainfall, which is also going to determine whether or not certain populations can live in an area. The thing I want you to think about weather as far as a limiting factor is that one of the reasons why weather is a limiting factor is because it really impacts space, food, and water. So an example that I gave in class is like, okay, let's say you have a bunch of mice living in a rock wall. And they really like living in that rock wall because it's next to an apple orchard. So not only do they have nice, cozy spaces to crawl into, but they also have a food source nearby that's abundant. Well, let's say a gigantic F5 tornado comes roaring through that field where those mice are in the wall, and it tears apart the wall, and it tears up the apple trees. So this is an example of weather being a limiting factor because specifically it's going to take away their living space, it's going to decimate their rock wall, and it's been tearing up the trees that have provided them with their food. So while weather can be a limiting factor itself, it can also impact food, water, and shelter. So it sort of goes hand in hand with those things. So just to recap our notes today, studying populations, we discussed how scientists determine population size, and 4 ways that we discussed are direct observation, indirect observation, sampling, and mark and recapture. Then we discussed how populations change in size. The most The main way in which populations grow is through births, and the main way populations shrink is through death. The birth rate is the number of births in a population in a certain amount of time, and the death rate is the number of deaths in a population in a certain amount of time. If the birth rate is greater than the death rate, your population size is going to increase, and if your death rate is greater than the birth rate, your population size is going to decrease. We also discussed the difference between immigration and emigration, and we've discussed limiting factors. What are the things that keep a population from growing out of control? And those would included food and water, space, and weather. Now that we're finished with our notes, please make sure that you write a summary. And again, your summary should answer the 3 essential questions that we started our notes with today. Thank you very much for listening, and have a good day.